Hi, this is Mr. Max. So this is part 3 of my video series on matrices. So what I'm going to look at here, I'm going to look at the determinant of a 2 by 2 matrix as well as the inverse of such a matrix. So first I'm going to start with the determinant. Remember, it's just a special number that can be calculated from a square matrix, that is a 2 by 2 or 3 by 3, but I'm going to focus more on a 2 by 2 matrix. And also we represent the determinant either by matrix A, capital letter, then it's bolded, or you draw a line underneath it, or you put it in bars like this, or you can just say det A here. The determinants are used in inverse matrices and the solutions of simultaneous equations. So we're going to do simultaneous equations. That's going to be part 4 of my video series on matrices. Now, remember, the determinant is just a number. It's not a matrix and only exists for square matrices, 2 by 2, 3 by 3. And it can be a negative number as well. So sometimes you will calculate and then you realize the determinant is 0. In such cases, when the determinant is 0, we are saying that the matrix is singular. So in these other instances where the determinant is a number, whether positive or negative, we say it's a non-singular matrix. But remember, when the determinant is 0, the inverse of such a matrix will not exist, and we are going to look at a solution or a problem with that regard. So in short then, if you have matrix A with the elements A, B, C, D, then the determinant of such a matrix is you take AD minus BC, where AD is referred to as the leading diagonal and BC, I'll refer to it as the trailing diagonal. So let's look at a few examples. So what I have here is I have 4 matrices that I want you to calculate the determinant of. So I'll suggest maybe you can pause the video and then you can also try to solve them on your own. Right, as for the first one, when we calculate, remember you take the leading diagonal, which is that 0 times 5, obviously giving 0, and then we subtract with the product of 6 times 4 or 4 times 6. Either way, the determinant is negative 24. As for B, when you find the determinant, I got to calculate it as negative 25. That is negative 5 times 2 minus 3 times 4. In this first instance, remember I said if the determinant can be a negative number, and this A and B are typically non-singular matrices. So when you do C, you should arrive at 27 as the determinant. But something interesting is happening at D. You realize the determinant is equal to 0. And once the determinant is equal to 0, we will see that this matrix does not have a inverse when we do the inverse later on. So this is referred to as a singular matrix, where A, B, and C are non-singular matrices. So let's bring in the inverse of a matrix. What do we mean by the inverse of a matrix? Now remember, whenever you have a normal number and you multiply any number by its reciprocal, let's suppose you take a number, well, it could be, I'm going to bring up an example here. All right, in numbers, when we take 5 times its inverse or its reciprocal, we get 1. So the inverse in matrices, when you get a 1, it's the identity matrix. So when you multiply a matrix with its inverse, you are supposed to get an identity matrix, which is the matrix 1, 0, 0, 1 here, okay, for a 2 by 2 matrix. So that is the way we are going to check one solution to test to see if this concept is true. Right, so I have matrix A, just to come back to the formula, and we have got A and D. I use colors here so that you can see if you find the inverse of such a matrix, then you put 1 over the determinant of A, and you find the determinant of A by saying AD minus BC. That is going to be the value here. And you swap the two leading elements of the leading diagonal. So the A comes under and the D goes up. And B and C, you're just going to swap the signs. So if B is positive like here, and you're going to have a negative, because a negative times a negative gives you this obviously positive, but if B is positive, then it becomes negative. If C is positive, it becomes negative as well. So if you have a 3 there, and now it's going to become negative 3, and if you have a negative 5 here, it's going to become 5 here. Okay, so there are many ways that you can write this. What's important is you swap A and D and change the signs of B and C. And here you have 1 over the determinant, which you can calculate. So I'm going to use the same examples from my previous exercise, and I'm going to find the inverses of those matrices. All right, so you can well pause the video here and try to see if you can calculate the inverse of these matrices in the event they do exist. Remember, they don't exist if the determinant is equal to 0, because if you have 1 over 0 here, you cannot divide by a denominator of 0. Right, so the first one, we already know that the determinant was negative 24. And what I did here is you swap the 2, the 0 and the 5, and you can see the 6 and the 4 here in the trailing diagonal. They're positive elements, and now subsequently they become negative. You can leave your answer like this as well, or you can go ahead and multiply each element there by 1 over negative 24. And that will give you these particular values here: negative 5 over 24, 1 over 6, 1 over 4, and 0. Well, if you try to do this one here, remember to swap the leading diagonal. If negative 5 comes under, the 2 comes on top, and these are positive 3 and 4. Now they become negatives. And you can also get the answer as negative 1 over negative 1 22s, and 2 negative 3, negative 4, negative 5. Or subsequently, you can multiply that negative 1 over 22 into each element, and you arrive at this particular solution. If you are doing C, you should also arrive at 1 over 27, and you swap around the terms, and this negative 9 becomes positive 9, and negative 7 here becomes positive 7, as you can see with the green that I indicate. Well, you can also leave your answer by multiplying throughout each term there by 1/27. Now what's interesting here is when you are finding the determinant of D, you realize you get 1 over 0. And because the determinant of D becomes 1 over 0, there's no point in you multiplying or in you finding the inverse, because the inverse of D does not exist as the determinant is 0. Okay, let's quickly check, and I'll take part C of my previous question there, and I will multiply matrix C times the inverse and see whether it gives me the identity matrix. Remember, the identity matrix for a 2 by 2 matrix is 1, 0, 0, 1. Okay, so let me just bring them in here, and we're going to multiply. So I suggest again that you pause, and you know when you multiply, it's row column. That's the order: row column, row column. So first row, first column here, and so on. Well, if you have done it, I've tried to write it here for you so that you can see it in different codes. Now you can grab your calculator and you can work out the first element as the second element, and the third and the fourth. If you do that, you will arrive with the identity matrix. Okay, so the next video that I'm going to upload will be on how to solve simultaneous equations using matrices. Okay,